here is the introduction to Class 8. We're dealing with the kinetics of particles, work and energy, conservation of energy. Okay. So we are moving on to a new chapter. So let's go to the bottom line up front. This section combines sections 13.1 and 13.2 because I prefer to, well, I'll describe this in a second, what the book does. So here's what the equations that we're looking for. We have kinetic energy plus potential energy plus some work that's taken between two states. Okay, so you notice there's a subscript 1 and a subscript 1 here for the KE, kinetic energy, and the PE, potential energy. Well, the work takes place between those two, between a state 1 and state 2. And you'll see on the right-hand side we have kinetic energy 2 and potential energy 2. So you can think of this as having a before and an after. So we sum up as like, here's all of the energy that we're seeing involved at a particular state. Then something will happen to it between states 1 and 2, and what results on the equal sign is what the new energy is going to be. And that something is work, which we define as force times a distance, but not just force, any old force times a distance. It's force dotted against a distance right there. And that dot means that the force and the distance need to be, it's only the part that's in line, right? If the distance is over here to the side and the force is right here, and if they're 90 degrees from each other, right? If something has a force that's been applied, like right here, but it moves in this direction, no work has taken place. It's only the amount of the force being projected onto the distance. So the force and the distance need to be in line with each other to be able to create work. So you'll see that Newt Dog right here is pushing this apple wheelbarrow, but it's only the distance that the thing is actually moving, right? That's the one. Now we can have a torque, like we apply a torque onto something, and we have a moment arm. So we have a force that's going out here and a distance right here. But if this thing doesn't move, no work has taken place. Only when the thing starts to rotate and the force is traveling through an arc, through a distance right here, that's where work takes place, right? So it's important to designate, even though work and moment have the same units, and that's force times the distance. In this case, work is only the distance, the force times the distance is traveling through. And kinetic energy for a particle is defined, and you might be familiar with this, 1/2 mv squared. It just rolls off the tongue, right? It's 1/2 mass times the velocity squared. And that's going to be the kinetic energy of the thing. Potential energy, we see this actually only gets introduced in section 13.2. I'm combining them together, introducing it at the same time. And potential energy is really a special kind of work. You could think of it as a special type of work where the path doesn't matter. It doesn't matter how you get from one state to another. And so that kind of work occurs. It occurs with gravitational potential energy, where I'm lifting this thing up. The potential energy here, right, and to here isn't any different from here to right here if these two are the same horizontal level right here. So it's a vertical change right here. The horizontal movement doesn't matter any. It's only because gravity is aligned only going straight up and down. So the only amount of work matters is the one that's in line with the force. Gravity is coming this way, so the direction of motion is up and down. So that's a particular kind of work as potential energy, and a change in potential energy. The same thing true with springs. Springs don't care what distance they go. They just know about how much they've been stretched. So the path that it takes between states 1 and 2 don't matter, only the amount of stretch. And so those are two types of works, potential energy, for gravitational, which I give a subscript G, and for springs, where I give a subscript SP most of the time. I'm trying to be consistent right here. So you see that the potential energy can turn into kinetic energy, and that's the conservation of energy when there's no external W. So I've given you a lot of stuff at the bottom line up front, but maybe this is a good condensation, and you don't need to like watch it any further. So like, totally got it. But let's get some more detail going on right here. I'm going to pause the video because I forgot to print out the thingy. We have to ask, what is work? And I would say as an answer that it's force through a distance. So they like to use du. I like to use dw sometimes. I don't know if I'm consistent with that. I kind of go back and forth. I think in my equation sheet I used a w. I don't like w because that's like weight we use it for. So a lot of times I'll use the capital U, but we want a dot. Remember, the dot product is a scalar product, right? And so we're doing a dot, and if you recall, that can often be seen as a projection of one thing onto another. So that's the incremental amount of work, and you notice it's a scalar, right? So energy is a scalar. The dot product is another. It's called a scalar product. It robs away the vectory parts of the force in this. So we want to try to find it between two states right here. So we go F dotted against dr, and we integrate across from there. Now, if F is constant, it's off. So if it doesn't change with the R right there, it's nice and convenient to just say F times delta R, or I even just think of it as X. Right now, it doesn't necessarily X. It could be S. It could be Y. Whatever distance that the thing is moving right there. But if it's constant and it's already in line with each other, we use this. Recall what the scalar is also the scalar product. That's what I meant to put on here. It's the scalar product. Work is caused only by the force that's in line with the motion. That's something I've often mentioned already right here. So if you had like a, so you see this force right in here, it's only, if this is moving to right here, it's only that the force that's in line with that motion right here. So you could break it apart into a normal and tangential that's onto right here. It's only this amount of force and that incremental distance that it's moving right here. We could say something, this is work by a non-conservative forces, and by what they mean by that is that when you have something that says well, work done by non-conservative forces means the path matters, right? So as opposed to conservative work, if the work is independent of the path, we say that's a conservative thing right here. So like they show this path integral right here, or it's like a circular integral, which says that like we're going to integrate all the way from the beginning to the end. And if the force is a conservative force by definition, then when you integrate it all the way through the path, if it returns right back to the original spot and the energy was zero, right? The net energy is zero. That means it was a conservative force, and that's really the main two types that we have when it happens is gravity and springs, because the gravitational force, it won't matter when it comes to the work where we put the coffee cup over to the side or whatever. It's only the up and the down that matters. So it didn't matter what path we took to get to there when it came to the kind of work that goes on right there. And it's pretty much because in this case is because the force is always in line with the vertical, so it doesn't matter the distance that we travel over to the side. So we can refer to these as potential energy. And the book Weights until section 13.2 to introduce potential energy. They start off in 13.1, and all the homework's in there. They consider the force, gravitational force, or the weight times the distance as work, and they only introduce potential energy later on. I think it's easier to just go ahead and introduce it in this class and merge the two sections together, as opposed to waiting. So potential energy can be written out as mg, and let's say y, right? We could also say that it could be weight times y, or sometimes weight times the height of the thing, we might say. And spring is 1/2 k, and I like to use a del squared, right? Sometimes they will write 1/2 k x squared. The thing is, this is spring stretchiness, so it doesn't have to be in line with any coordinate axes. It's only the amount of stretch. So I prefer to just say del, where I'm going to write this down below anyway, but here's my spring unstretched right here, but then like it gets moved right here. Here's what del is going to be, right? It's the amount of, here's the original length, we could even call LO right here, right there. So like someone could say that this was x right here, and that's why I don't like saying it's times the square root of x. Only this amount of del, which is, I'm saying, the displacement del. For gravitational work, right here I try to make the point that like the external work that we're placing through there could be mass times gravity times y2 minus y1. I'm looking at my time onto here, 12 minutes. That's happening to us, right? So we have external work that's taking place or being drawn out of the system. So as we're coming up, depending whether we're coming from state 1 or to state 2, but if we are requiring work to come up, it's going to be in the opposite direction of the motion right there. So the force is coming down this way right here, so that's the negative right here, but we're coming from state 2 is our final thing, and our state 1. It's easier, I think, to think of this as a storage of energy, though, as opposed to trying to mess around with the signs of this. So I say that we just have at state 1, we have mass times gravity times the position at y1, and then we have mass times gravity, the position at y2, and it's best to create a datum. Which is to say, here is the datum right here. And then we will just say that that's going to be 0, right? Where the datum at y1 is 0, right in here. So that when we get up to here, right here, we've moved upwards this amount right here, right? So that says this is 0 if that's the datum right here. So what we've had to do here is we've required work, right? So it's going to be negative. That's what I'm saying right here. It is in terms of the negative sign, is that we've required work. Work has had to come out out of the system in order to do this. But generally speaking, it's going to be easier just to think of it as a state that we have to have. And in a similar way, you know that the spring force can be equal to K, and I'll go with a del right here, even though they're using x's right here. Here's the x state that they're saying of these different places right here. But spring force is just, and maybe I'm going to write that this is a del right there, or as part of that. I guess I'll leave it as X. We decided to keep it in there right there. So what we can say is that the incremental, that's supposed to be capital U, is going to be Fs times, I guess I'll go dx. So maybe I will leave this as x for right now, but I prefer the del when we get everything said and done. And so we're going to integrate that. We find that Fs right here, and let me replace that Fs with what's up above, so that kx dx right here. So, and we're going to go from x1 to x2. So what we find, we get 1/2 k x1 squared minus 1/2 k x2 squared. And that doesn't make any sense to me. Why did I write it out that way? I think it should be the other way around, right? Yeah. I don't like that I wrote it that way. I'm fixing it. Oh, I see. It's because he put it as a negative x. Why did we put it as a negative? I don't know what the point of that was. Putting that in that way. I guess what we're showing right here is that the force is negative as we've drawn it right in here, right? So the force is coming back in that way right there, but we've moved it this way, I guess. So I guess that's the one where it makes sense. Okay. I think that maybe that's more confusing than it needs to be, to have it as being negative. But I think that because we're showing it is drawn connected right into there. I think of it as being the area underneath this curve right here, right? So it's force times distance, and that's the area underneath the force distance curve right there is what work ends up being. And we can, in writing it as a potential energy, we call it 1/2 k, and I say del 1 squared, and 1/2 k del 2 squared right here, where I'm going to say that the amount of stretch is going to be del here. Right, so you just need to know about the undeformed length right here and the position, and figure out how much longer it is, or shorter, because this also will work in compression right here. And what we've really found right here is the amount of energy that's going to be stored in the system from right there. And they're playing around with that negative work here because they're talking about whether something's in or out of the system. Work done. Let's see. I'm going to try to wrap this up here shortly. All right. So other work that we might need to done. Work done by a normal force. Well, if we have this Fn that's taking place right there, and maybe a W right there for the weight onto the thing. If the thing doesn't move, it's going to be equal to 0. Well, all right, so if there's a normal force, which is typical here, normal force doesn't do anything. How about work done by a fixed point? Well, you put the force on there as much as you want to, and it's 0. It's like if this is fixed right here. Doesn't matter if you're pushing up against a wall. You're pushing up against the wall as hard as you possibly can. If the wall doesn't move, you didn't do any work. Now, we could say that there's maybe some flexibility in your bones and whatever. Nah, it's just you still really haven't done work. How about work done by friction? Work done by friction is negative. Why? Because the motion of the piece right here, right? So see, this box is moving in this direction. Friction is coming down in the opposite direction. So Those force vectors are opposite direction from each other. They're dot producting against each other. That's one way of thinking. Another way of thinking is that friction is energy that is being robbed from the system, right? It's an external energy loss. Looking at that hair right there. Where'd he go? Right there. He's not coming down. All right, we're going to leave him. Okay, so now we're continuing on with section 13.1b here. So we come back and we look at the principle of work and energy, and we're going to go all the way back to Newton's second law. Remember that Newton's second law did not say F equals ma. It said the sum of the forces is equal to the time rate change of momentum, which was going to be dmv dt, right? But we recognized that mass is going to be constant here. So in the tangential direction, what we have for F equals ma is F equals times the mass times the acceleration in the tangential direction right here. So you'll see that it's right in there, right? That's the same thing we're repeating right here. We could use the chain rule as part of this right here and see that we have this right here, right? ds, d right here, that we have, I'll also say that this right here is going to be v, velocity, right? So really we also know from another way of writing out what the acceleration is going to be v dv d position. Sometimes we say dx right here. So what we could do is we could rewrite this thing out here, bring the ds over to the other side. Now remember that the force and the distance are in line with each other, right? So that right there is a kind of work. A kind of work is taking place. So we can integrate both sides onto this thing. And we're saying that this guy right here is some type of energy. Some type of energy is taking place. And if we do that, we can say between velocity 1 and velocity 2, right here, mass, and then we had velocity dv, we can say that we have 1/2 mv2 squared minus 1/2 mv1 squared right here. And I keep writing it the wrong way for some reason. I don't quite understand why I keep writing it onto here. But anyway, we can declare what this is right here as kinetic energy 2 and kinetic energy 1. Right? So we define kinetic energy as 1/2 mv squared. And we can see that it came from Newton's second law. Right? All we did was to integrate the velocity part of the thing. And so now what we could do is we could use all these things that we had together and state as a primary equation that we have the kinetic energy at state 1, the potential energy at state 1, the external work that's taking place between states 1 and 2, and the kinetic energy at state 2 plus the kinetic energy, I said potential energy at state 2. And it's really just an energy equation, energy equating thing, or energy accounting thing. It's like we say. So in thermodynamics or in fluid mechanics, we'll also see that there's these other energy equating, accounting type of equations. But here for solid mechanics, we have these two types of energies: kinetic energy, the energy of motion, potential energy, it's like a stored energy, and then we also have this work that can be placed onto the thing. So we know there's 1/2 mv squared, we have mgy, and we can also have 1/2 k del squared, and then this is really just going to be force times the distance between 1 and 2 that gets moved. And then I think the last thing before we have examples, we should get more examples. We want to talk about the principle of the conservation of energy. And that's no external work or losses. And so that's just simply KE1 plus PE1 is equal to KE2 plus PE2. And so there's a trade-off. There's a balance going back and forth between this kinetic energy and potential energy. And so especially when there's no frictional losses, there's no force coming from the outside and pushing onto the thing. So you might see in this little pendulum guy right here, it's like when is potential energy a max? Right here. And then where is kinetic energy a max? Right in there. And then once again, right in here too is where potential energy is a max, right? So we have zero. If this is where it stops right here, if we start it from right here and we let go of this ball and he starts to move down right here, at here he had no kinetic energy, so this would be 0, but this would be at its maximum. As it's moving down, it gets down to here, and that's a good place to say that is the datum right here, right? Because now we could say potential energy right here is going to be 0 right here down here, and kinetic energy is at its maximum. So all of the energy is now kinetic energy because we've established that's where the datum is, where we're going to say that's where the 0 for potential energy is going to be. And then as it's moving up, it's losing kinetic energy, but it's regaining potential energy. So one strategy we might want to do is to have different states and move between them, and 1, 2, and 3. We could have so we could see that we have this box, and some people like to have a datum maybe that's somewhere in the middle, but I don't like to have negative potential energy. So I like to find the lowest spot and state that as the potential energy. Or you might just want to reset it. Like you might go between states 1 and 2 and said, but the next thing that I go is it's actually going to be more useful. Okay, well, let's reset, and we say, well, now the new datum is going to be at a new spot. But I like to keep it as the lowest spot on there. So there is pretty long, 27 minutes. Maybe need to condense that down a little bit. But anyway, that's the main idea for class 8.